most of you don't know me. I grew up in Switzerland, like speaking French and German. Went to EPFL, did a short stay at MPAR working in the lab on organic solar cells. Then I joined IBM, and that's where I did most of the work that I will be presenting today, doing an MPhil in Cambridge, having Alexei as an internal examiner, so yeah, and then a PhD at the University of Bern. And since last year, in February 2022, I went back to EPFL, and there's where I lead a lab for digital chemistry. And within this 1 year, like, my team grew a lot. So I have 7 PhD students, 1 postdoc, and it's super exciting. You know, it's what keeps me going to EPFL every day, just these interactions with all those brilliant people. Today, I'm talking about machine learning for organic synthesis, and what I have to talk about first is really the data representation and models, then how we can use that to build tools for AI-driven organic synthesis, and then we have a few minutes for an outlook and questions. You all know, you've already seen this number today, so if we think of the number of molecules that we can synthesize, it's nearly endless, 10 to the power 60 if you take drug-like molecules. And machine learning tools can help you at different stages of the molecular design cycle. We can, on one hand, ask the question, what molecule do we want to make? And we've seen like so many like inverse design algorithms popping up in recent years, but what is often missing in the end is the experimental validation. And one reason for that is that synthesis planning is not that easy. And this was one of my main focus in the past, and still one of the focuses of my lab today, to accelerate synthesis using machine learning. If we take one random literature reaction as an example, we can imagine different tasks for which that machine learning could help you. For example, we can try to predict the most likely product given the precursors. We can turn it the other way around, and as we've seen in many talks today, like do single-step retrosynthesis or multi-step synthesis planning. Then we can also provide additional information if we have a training set to train on that, like a reaction class, a yield, selectivity, and something I will just touch on briefly is atom mapping. It's like a useful information to have for chemical reactions, basically to know which product atom is mapped to which reactant atom, and using that we can extract automatically the reaction center, as was shown by Alexei this morning. So yeah, the big question is, where does the data come from? And this is the most important part in machine learning. And we have huge databases such as Reaxys that collected high quality data for a long time. Then we could imagine also to integrate sources, ELNs, high throughput experimentation data, but they often cover like a much smaller space of chemical space, and we can augment this whole thing with simulations, and also we have in open source accessible like patterns, and I find this a great source because like the models we can develop on this rather low quality data, we can then also apply to other data sets and basically like kind of but still show the results of our models in open source. And there I'm really thankful to Daniel Lau, who text mined the US patents and made this huge set of reactions available. Contains roughly 1 million, 1.5 million reactions depending on how you deduplicate it. And one way to represent those reactions are reaction smiles. And this is, it doesn't contain context information, but it contains the graphical informations of those molecules. And here you have the corresponding 2D depiction, and here with atom mapping, so this additional information. And using that representation in the last few years, we could do this analogy to human language and basically represent our atoms as letters and molecules as words. And in the end, if you split those reaction smiles into sequences of atoms, what you can do is borrow methods that were developed for human languages and start to apply them for chemistry. And the go-to architecture there is the transformer architecture. And this is what you have, for example, behind Google Translate, this encoder and decoder that would learn a function to translate from one language to another just by seeing examples. Now what became really popular in recent weeks and months is if you only look at the decoder here, this is exactly the architecture that you have behind GPT and ChatGPT. And this is really a language model that learns from seeing a lot of examples. And during my time in Cambridge, I worked on a molecular transformer model that learned this function to translate from reactants to the product, most likely products. And back then, without integrating any rules or additional chemical knowledge besides those smiles, it's kind of, it could perform better than other approaches in reaction prediction, at least on the common benchmarks. When I went and transitioned to the University of Bern, we asked a bit the question, what is missing in reaction prediction? And two things that were obvious is stereochemistry and experimental validation. And to work on that, I teamed up with Giorgio, who you see here, and he went to the lab, performed the 14-step synthesis of a lipid-linked oligosaccharide, and on this test set and two other test sets, one coming from Reaxys, we could basically show that our model that was fine-tuned on this specific small data set using transfer learning could actually perform much better using only a little data set. This is just to show you one example of a glycosylation reaction that came from a JAX test set, and it's really the fascinating thing there was that even for a human expert, it would not have been obvious to predict whether it reacts in equatorial or axial position, or whether it would form an alpha or beta bond, and this was correctly predicted by the model. And the cool thing here is that similar transfer learning approaches can be applied to any reaction subspace of interest. Something else we looked at during my time at IBM Research, and I'm still continuing to work on at EPFL, is retrosynthesis. And yeah, it doesn't need this introduction slides because we talked a lot about the retrosynthesis during the whole day. But yeah, you want to go from your target molecule to known commercially available building blocks and do this step by step. And you want to have machine learning models that can help you to suggest really diverse routes, because often there's not one correct route, but diversity is really key. And our approach was kind of fully rule-free. It was just like the models learning from a lot of data and having those chemical rules implicitly encoded. But yeah, this I think it was part of a whole vision where we tried to go towards automating chemistry. And yeah, imagine you're a chemist at home, you do the design of this target molecule, then you connect to the cloud, and you get access to synthesis planning, which could be like that tool, but also similarly Reaxys API and or web application. And then you have another tool that converts all the different steps that you have in your route and suggests initial conditions that you could try. And if you have that, you can really go on and connect it to a cloud-connected synthesis platform, or just go there and run the reaction yourself in the lab. And at this point, let me just highlight Theodor Leiner and the whole Rob Erickson team from IBM Research. My part was really to work on the machine learning models and kind of far away from the hardware, but this requires kind of a lot of engineering to get there and do this whole pipeline. So yeah, what we've seen in the first few minutes is really like how language models, large language models in a encoder decoder fashion can learn translation functions. This can be from reactants to products. It can be the other way around, or even like the model I was mentioning quickly, like that converts the reactant smiles to like this synthesis steps that could then be automatically executed. It's also in similar fashion a transformer that, yeah, direction transformer model in encoder decoder fashion. What we can also do is just use the encoder part and then predict one single value or output, and we can do this in reaction classification or yield prediction. And to look at that, let us first zoom into what this transformer model actually is. Here you have an encoder-only transformer, and what this is made of is stacks of self-attention layers. And what it gets as an input is just this tokenized reaction smiles. So the smiles atom by atom into that model. And also GPT would be kind of very similar to that model, but just be trained on a different pre-training task. And then every layer has kind of, this is a neural network architecture, and it has like multiple heads. Those are like kind of sub-parts of the models that can learn different functionalities to get better and better representations of the individual tokens you have in the inputs. And from that, as soon as you have contextual representations, you can use that model to fine-tune it, to specialize it on different sub-tasks or downstream tasks. You might ask why this context is so important, and this is really why those models are really successful. You could go back to human language and imagine like the word bank. The word bank has a completely different meaning whether you speak about the river bank or the bank you get money from. And this meaning is really like obtained by the context of the word. And that's why like I think those models are really good at capturing like and understanding what goes on in those sequences. And we can look at it also from a chemistry perspective. If you look at those two first carbon atoms that you would have there, they also, their actual meaning depends on the nearest neighbors in the molecular graph, on the complete molecule, on the reaction, and yeah, that's really the strength of those models to capture this contextual representations. Just a few examples. Reaction classification is just we want to go from chemical reaction directly to some kind of class that where the chemist gets a lot more like information from, and if I tag as predicted reaction with the corresponding class, a chemist might already have an initial point to start from when he or she they want to like run it in the lab. And yeah, we could show that on data from Nextmove software, we could build actually quite accurate models. But what was more exciting for me in this work is that if we cut away this yellow part, the last classification model, what we could do is just get the embeddings, like the vectors out of this encoder part, and use it kind of as a fingerprint for our reactions. And this allowed us to like build up chemical reaction atlases and kind of turn those discrete objects that you have in those chemical reactions into a continuous vector. And I think this is really interesting also to have a different way of searching for chemical reactions. For example, if we predicted this reaction here, this is just an example from the IBM research web platform. Probably it has changed in the meantime, but what I found super useful is that you could basically predict a reaction and then look at the most similar reactions in the training data of the model, and kind of if you had more information, context information available for those reactions, like the procedures, you could also get back to that information. And I find this is a very valuable thing to do with those reaction fingerprints. We tried other things like the prediction of patent reaction yield, and just long story short, it didn't really work for us. So there was just too much noise in the patents, and we have a few ideas how we could improve, but so far the only like global reactivity model I've seen is from the team with Jörg Wegner and Paulo Neves at Janssen that basically used Reaxys data to train that. And Paulo now joined my lab in a partnership with Janssen, and I'm super excited to continue working on similar things. What worked, on the other hand, is when we went to super high quality data that comes from high throughput experimentation. And again, it's not a super simple task, I would say. You basically trying from this textual representation of those molecules, of those reactions, you're trying to basically train a model to predict the corresponding yield. And but compared to what had previously been published in the literature, like our transform models performed quite well on this high throughput experimentation data from the Doyle group, Buchwald-Hartwig reactions. If you hear like deep learning, usually you think it requires quite a lot of data, and also there we try to reduce the training data and could show that even with like only 100 data points, we were kind of performing similarly than random forest and DFT calculated features. So this was kind of exciting for us, and we asked the question, why do those language models work so well for chemistry? And there we tried to really like dig into the model and kind of see what is going on when those language models are trained on chemical reactions. And what we discovered is that they were basically capturing, without being told to do so, how atoms rearrange in during the reactions. And this is exactly what we had like at the beginning, this atom mapping. And using that signal, we could develop a reaction mapper. And what this gives you is basically, from any kind of unmapped reaction that you might have in your database, you can quickly get the atom mapping. And the really nice thing there is that even on an independent benchmark, reaction mapper was ranked best, and kind of like with double the accuracy of the open source alternative, and even better than some commercially available tools. And this is just available for free online. Yeah. Just a quick summary of this first part, and then a bit of an outlook. You've seen a lot of transformer models. It's kind of the things that stayed for the last 5 years in machine learning. Somehow it's kind of like everything changes at such a high pace, but the transformer model stayed, and it's been useful for many different, like very specific tasks in chemistry. Now in my lab, we do kind of, we broaden a bit our horizon, something that Alexei is an expert in, but that we got a lot of requests, and it's like, can we optimize chemical reactions? So I have Bojana Rankovic, a fantastic PhD student, working more on like Bayesian optimization for chemical reactions, contributed to the Gauche library, which develops some specific kernels or makes them a lot better available for like chemistry applications, for molecules and chemical reactions. And we're looking at kind of, we've seen also in Alexei's publication that one-hot encoding, which just basically tells you whether like a component is here or not, gives you like kind of a super high performance in most of the very constrained data sets for reaction optimization. And so we went on and took some data where this could not perform well and kind of tried to like go beyond that. And it was kind of challenging, but I think we are getting there, and we'll have an updated version of the preprint and the publication out soon. What worked really well, and this is just to highlight some work together with Daniel Probst, this kind of heuristics fingerprint called DRFP, where we take a symmetric difference between the precursors and the product set. It's a bit fast, but I'm running out of time. So another project I wanted to highlight is from Olli Schilter, where he tried to design new Suzuki cross-coupling catalysts with the metal as well. And it's this typical VAE approach inspired by the automatic design paper by Gomez Bombarelli. And the really cool thing that he could show is that when he activated this predictor part during training, we could really structure the latent space and have some, this energy distribution where we could really pick like the catalysts in the right energy range. Last thing, GPT-Chem recent preprint with Kevin Jablonka, fantastic. It's mostly done by him, and it's really about how can we combine human language, low data, chemistry tasks, going for classification, regression, but also inverse design, like design me a molecule with this particular property, and combining everything into a GPT model that is fine-tuned, and with only a few data samples, usually is at least like comparable to specific models that are really trained on those tasks. But it can just do everything like that. And with this, I think that's the key message is really that those language models will certainly stay here for the future, also in chemistry, and my group is super excited to also work on them and many different other topics to try to improve sustainability in chemistry. With this, I highlight all my fantastic collaborators I had in the past, and thank you very much for your attention.